Hello and welcome back to our series of lectures on shaft design. Um, as we indicated in the previous segment, our objective now is to put the entire story of designing for power transmission systems. We want to put it together with a bunch of examples so we can illustrate how we will proceed with the design process. So in this segment, I'm going to discuss how we're going to estimate shaft sizes and support and layout in order for us to meet design requirements related to stress levels on the entire shaft. In segments that will follow this, we will go more into detail of other requirements such as deflections, and then also the requirement of reduction of vibrations. This will be a continuing long type of design requirement that will just go on for a while. So it will have many segments in which we're going to analyze the design for a counter shaft in a gear reducer system. As you will see that some of the critical issues will relate to the presence of stress concentrations, and those stress concentrations occur as a result of the need and the necessity to attach gears, for example, to shafts. In order for us to attach a gear to the shaft, we have to locate it precisely at a certain location, and that is usually done by reducing the size of the shaft or increasing it to create a shoulder, and the gear is resting against the shoulder. So that will create a stress concentration area. And moreover, we will have to make the gear such that it doesn't get loose, and that is usually done by some kind of keyway and a retaining ring. So if we put the keyway, then that will be under a torsional stress that will also be amplified by the fact that we have to dig into the shaft and generate this groove for the keyway. And the same thing also will take place at retaining rings. So in other words, the fasteners will play an important role in shaft design, as we will see here. So the first step is to be cognizant of how to find the stress concentration factors. And generally these factors depend on the shaft design, which is not known a priori, because we don't know what the shaft size is before we do the calculations. So the design procedure starts with an assumed set of typical stress concentration factors for tensile and shear type loading, and those will be improved or changed as we iterate and change the size and or the material for the shaft. So that's the procedure that we will have. So what we will have here is first is that you look here the stress concentration factors for the first iteration. We want to estimate the stress concentration, static stress concentration factors, K sub T for tensile loading, and K sub TS for shear loading. And what you'll see here is that there's standard requirements for shoulder fillets that can be either sharp, and the radius of the fillet is 2% of the small diameter, or can be well rounded and radius is 10% of the diameter. In these cases, we have estimates for bending type stress concentration factors, torsional stress concentration factors, and axial stress concentration factors. For as far as attachments or fasteners, then we would have to look at end mill key set and sled runner key set and the retaining ring groove. For example, sled runner key set, which will be used in this example, is 1.7 for bending, but the retaining ring is very, very high stress concentration factor for bending because it's typically very, very sharp, very small region, so there's an abrupt change for the retaining ring. So if we look here to understand a little bit more about the idea of shoulders and stress concentration factors, as we move on from the small diameter to the large diameter, then we would like to avoid abrupt change in the diameter of the shaft, and that can be achieved either on the small shaft side or the large shaft side. So we could gradually change the diameter by introducing a fillet depending on the philosophy of the design. And the idea is to kind of follow approximately the force flow lines as they expand from the small diameter to the large diameter. So you see here that in this case we have a sharp radius for the ball bearings, and then we can accommodate this expansion of the force lines by a large radius undercut on the large diameter side. Another method is to kind of mill the shaft with a region that has a shoulder relief groove of large radius, as you can see here. And also a third way is to actually go to the small diameter size and introduce a large radius relief groove. So these solutions are dependent on the exact design and the assembly and so forth. But as you can see here, maybe one of the preferred solutions would be the shoulder relief groove if we have the ability to mill the shaft in this fashion. Now next we'll see that once we have this shaft idea about the regions in which we have stress concentration factors, what we'd like to do is go through thoroughly a complete example and determine the size of a counter shaft for a speed reducer just on the basis of the stresses. As we mentioned, there are other design considerations that will come into play later on, so we will proceed with the same example in the next lectures to go from one design consideration to another until we complete the task of designing the counter shaft. So in this problem we have case studies. This is a part of a case study that will be used in later chapters. And in this case we have a double reduction gearbox design, and we want to develop a general layout and axial dimensions of the counter shaft. So the focus is on the counter shaft, and the counter shaft will carry two spur gears, and the way that it is proposed is in this fashion. So the counter shaft, we have gear 3 to be mating with another gear. So this is a large radius gear. The diameter is 12 inches, and gear 4 is only 2.67 inches in diameter. So the shaft is to carry these two gears, so this is required, and we need to design the shaft. In other words, we want to find the sizes and the materials, so forth. So the requirement is that the gears and the bearings, they are located and supported by the shoulders, so we have to have shoulders, and held in place by retaining rings. So that's a requirement. And then the gears must transmit torque, and when they transmit torque, they must be attached to the shaft, and they attach to the shaft through keyways. Therefore, we are forced to use the sliding keyway to attach the two gears to the shaft. From other analysis, we're given, so that's another part of the design problem, but here we're given that the forces are already known that are transmitting in the tangential and the radial direction. So each one of these two gears will have a tangential force and a radial force. So 2, 3 is the force between gears 2 and 3, and what we see here is only gear 3. So there's a gear 2 right here, which you can't see, and this gear 2 is transmitting a force to gear 3. And the force is not only it's usually at a pressure angle from the teeth of the gear, and the pressure angle gives it comes at an angle here, and this is analyzed to a radial component and a tangential. Tangential is into or out of the plane of the board, and therefore this information is also given to us. And as you can see here, for gear 2 transmits 540 pounds in the tangential direction and 197 pounds in the radial direction. Now, if you look at gear 4 is receiving force from gear 5, and this force has two components, but it's a large force because the diameter of the gear is small. So the small diameter will have to take larger force, and the large diameter will have to take a smaller force because the torque has to be the same. So if you look here, we have the tangential force from gear 5 onto 4 is 2431 pounds. That's very high. And the radial force is 885 pounds. And we would like to use those to find stresses and therefore design the dimensions. So the problem is that we don't know. We want to find all of these dimensions: D1, D2, D3, D4, D5, D6, D7. Okay, well, what we know are the dimensions of the gears, so we know that, and we know that we must support it with ball bearings on one end and support it with another ball bearing on the other end, and we have all of the dimensions that you can see in here. So we have a datum, and the datum is a 0, and then we choose points at critical locations. At C, that's the interface for the ball bearing. It's at a 1/4 inch. The center line is a 3/4 inch. The other interface is 1 1/4, and so on. So you can see here a number of locations. All of the dimensions are from the datum 0. So we have the axial locations of all points on that system. And we're going to give the points letters A, B, C, D, and so on up to here and at the other end. So the process begins with a free body diagram as usual. And so the process of design, first we're going to take the forces, put them on the gears, assume that we have no binding of the shaft at the ball bearings, and therefore the moment is 0, and therefore we can find the reactions very easily at the ball bearings. And we note that we have to work with two planes because one is force is coming in the radial direction, another force is going out of the plane, which is in the tangential direction. So we must construct the force system, which is the free body diagram. From the free body diagram, then we will get the information, and we will produce the shear force diagram, and then we will produce the moment diagrams. Note that at the end of the day, the moment there's going to be a torque distribution on the shaft, there's going to be a moment distribution on the shaft, and the moment distribution, moment is also a vector, so we think of moments as vectors. So we'll get two components of that vector, and then we'll add them up vectorially, so we can produce a distribution of the resultant vector of the moment that is distributed over the entire shaft. And then once we have that, then we can proceed with doing stress calculations. So as you can see here, the free body diagrams, we have the axis system. The X is along the shaft, the Y is in the vertical direction, and the Z is pointing towards U. And in this case, we know the W radial and the W tangential for gear 2. The same thing, W radial, W tangential for gear 5, from 5 on 4, gear 4. And therefore, we can take vertical equilibrium with 2, 3, and 5, 4. Sum of the forces equal to 0. Sum of the moments equal to 0 at some point. And solve these two equations to find that in the vertical direction, the reaction at the ball bearings to the left is 356.7 pounds, and to the right is 725.3 pounds. We would do the same thing for in the XZ plane, all forces on the XZ plane, to get the reaction in the Z direction at bearing A and the reaction at bearing B. So at bearing B, you can see that the reaction force is very high. It's the highest in this system. And once we do that, then we need to consider both torques and moments. So let's consider the torque first. The torque is pretty straightforward because the torque is the W23 times the distance to the center. And the distance of the center is the radius of the large gear. So W23 times the radius of the large gear, that gives us 3240. So that torque here starts exactly at the center, because that's where the force is transmitted through the keyway. And there's no other torques from G to I and up to J. J is the center of the second gear. So the torque is constant. And then that is, since the shaft is rotating at constant speed, then the torque that's produced by the tangential component of W54 times this radius of the small shaft, you can verify for yourself, should be the same, but in the opposite direction. Therefore, you go down to 0 torque on this side. So there's no torque beyond point J, and there's no torque before point G. Note that immediately after you find the torque distribution, then you would only, in the analysis at the end, you're going to select the points that have a torque, because we're looking for a combined loading. We're looking for a loading that has moment and torque at the same time. So that immediately excludes points to the left and to the right, and we have to examine eventually point G, point I, point J, and not point K unless we have to, which we might. So having done that, then the next step is to find the moments. And the moments, we cannot generate the moments without the transverse shear. And the transverse shear, we have two planes, the XZ plane and the XY plane. On the XZ plane, the transverse force starts from the reaction. So the reaction is 115. So we start from this point and build it up. So if you can see here, then you have 115 starting here. This is the basically the reaction, and then step it up as you add more force and down and so on, just like what we learned to get the shear force diagram. The bending moment diagram is the area under the curve, and the area under the curve, each area like this rectangle here will result, if you find this area, it gives you the value of the moment at this point, 230. So 230 is 115 times this length. It gives you 230 because m is the integration of v. And then you add up more area, so the moment is going to rise all the way to 3996, and then you subtract this area, and the moment will come down to 0 as expected from the equilibrium. And we do the same thing for the XY plane. So we have a different moment distribution, as you can see here. So now, as we mentioned, the total moment is the sum of these two. So this is a vector has two components. At every point, for example, this point here, we have 230 and 713. At this point here, we have 3341 and 1472, and so on. So what we could do, in order for us to find the magnitude, we just add up these two values in a vectorial way, like this. We sum them with the square root Pythagorean theorem. In between, we just don't care that much because in between it's not gonna add up linear, but we will just assume that it will be linear for the magnitude in between, because we are interested in the magnitude at some critical points. So if you look at point J, the value is the square root of 3996 square and 1632 square, and the result gives us the highest bending moment in the shaft at that point. So we're going to start with that because it has the highest bending moment. Not only that, but it also has a stress concentration at the shoulder, and at the same time it has a torque. So this we're going to examine potential failure points by ourselves. So we have to think about where things can fail, and the way to do it is by logic. So the logic is that we have the largest moment, there's some additional torque, there's also stress concentration factor, so it has to be that point. So let's check it, and when you check it, you find that we have here a moment that produces an alternating value because the shaft is rotating, and a torque that produces a mean value because that's always constant, while the mean value of the bending moment and the alternating value of the torque are both equal to 0. So with these conditions, we are ready to calculate stresses if we know the stress concentration factors. So for that, we have to do some assumptions. We're going to assume that there's a fillet radius for the gear at I, and from the table, we estimate the stress concentration factor KT is 1.7 and KTS is 1.5. And we're gonna ignore any effects of the notch sensitivity factor on reducing these stress concentration factors. So we're just gonna go ahead and translate them to the fatigue values directly without any effort at this point, because we're just taking the first iteration. So next, I need to select a steel. So when I'm going to select, as a designer, I want to save money, so I'm going to select the cheapest steel possible for this application, and it's cold drawn steel, so it will have lower strength, and therefore it will have kind of a low value of the fatigue lifetime as the endurance limit, and we need to correct the endurance limit for the Ghoniem factors, which is surface, loading, size, and so forth. And we don't know all of these, so we're going to do some estimation and then change as we know more about the size of the shaft. So if you can see here that this is the correlation we use for the one of the Ghoniem factors. But before we do that, we know that the steel, if we look at the tables, 1020 cold drawn, it has an ultimate strength of 68 KSI. So you would think that the the SE for that, if we're going to design the shaft for infinite life, will be half of that value, 34. However, if we make corrections, the correction for the surface finish, that machined, so it's 0.883, and the second correction we're going to guess, which is the size, dependent on the size, but we don't know the size, so we're going to guess it as 0.9. And then we'll take all of the other factors to be 1, and therefore our first guess at the endurance limit is 27 KSI. Next is to combine the loading conditions, and here we have an alternating component of loading that is being produced by the moment, and a constant component of the stress that is produced by the torque. This constant component is shear, while the alternating component is axial. So we have to add them up using the distortion energy criterion as the easiest way, and we're using Goodman criterion. So we have an equation for the diameter of the shaft at this point I, and the diameter of the shaft if we're designing for a safety factor of 1.5, and combining both the alternating and the mean value in the sense of the distortion energy, we obtain a diameter of 1.65 inch. So this is kind of our first estimate, and since it is not common, we have to look in the tables and find nominal values, and the nominal values, when we check, we find that the nominal value that is closest is 1.625 inches, and that gives us the diameter for one diameter for the shaft. So if we go back to what's happening here, we have required to analyze the situation at this point I here, and this gives us the small diameter, which is D5 basically. This is 1.625 inches. So the question to us is, what about this diameter? What about this? What about that? And so forth. So in order for us to proceed, we pinned one diameter only. So we're going to use some rules for shaft design in stepping the shafts. Well, one of the rules is that since this is 1 and 1.625, then we can take the diameter D7 and D1 to be smaller to fit the ball bearings, and those could be selected as approximately 1 inch diameter. Therefore, we want to step from 1 inch to 1.625, so we have an intermediate stage here, and then from 1.65 to the largest diameter. There are rules for stepping at these shoulders, and the rules is that we don't step more than 20% of the diameter. So once we figured out this is 165, then we can step it up to about 2 inches and step it down to about 1.4, and then the entire system is kind of determined. So we'll have 1 inch, 1.4, 1.625, and then 2 inches approximately. And then we'll do a complete analysis. If need to be done, we either have to change the material or change the diameters again. So let's just continue to see that. So as we mentioned here, a typical ratio for the expansion is 20% more. So 1.2 is the ratio. So the diameter, the largest diameter in the shaft is 2 inches. And then once we have this, then we assume a fillet radius of 10%. So 10% of the diameter. R over D is equal to 10, so 10% of the radius. And that can give us more exact stress concentration factors, because we have R over D equals 10% and D over D is known already 1.23. So from the figure A15.9, we find that the static stress concentration factor is 1.6, and then also from the figure 620, we find the notch sensitivity factor to be 0.82, and we continue on to convert the static to a fatigue via the notch factor. So the fatigue stress concentration factor now is 1.49, and the same thing for the shear component of the stress concentration factor under fatigue. And then once we do that, we have sizes. Then we can go back and check on the Martin factors, the K sub A, which is a machining part. The surface didn't change, of course, but K sub B changed, so the diameter is different. Therefore, we re-estimate it to be 0.835, and then re-estimate the endurance limit. Then you see that it dropped down from 27 down to 25, which is a change that is to be carried through. So based on that, we recalculate now the alternating value of the stress from the alternating value of the moment at this point. So we come to almost 13 KSI, and the mean value of the stress, note that I have a factor of 3. This is in the von Mises because we have shear, like we add the shear with 3 times tau square. So this is basically converting the shear to an equivalent von Mises stress. So it comes out to be 8.7 KSI. Once I know that sigma alternating, sigma mean, and using Goodman is the easiest way, then we calculate sigma alternating over endurance limit, sigma mean over endurance limit over the ultimate, and that gives us 0.62. From that, we can solve for the stress concentration factor for fatigue. I mean the safety factor for fatigue, and find that to be 1.56. So it's above what is required, and we have satisfied the requirement, fatigue infinite lifetime requirement at this critical location I. One more thing we have to do is check to see if we will exceed the yield on the first cycle, and this basically finding the maximum stress, alternating plus mean, and then comparing that to the yield. And we do that, we find that the safety factor for yield is pretty high. It's 2.64, so there's no particular issue with the with that type of requirement, design requirement. Then next we check the diameter at the end of the keyway, just right to the right of point I, and at the groove at point K. So we need to check a little bit more. So I will show you here if we have satisfied now the design requirements at this critical point I, but we need to check at point J because it has a keyway, and and the keyway has a stress concentration factor. Not only that, so J is the last point that has a torque on it. It has torsion, so it could possibly have a problem different from point I. But point K, the moment is small and the torque is 0. However, point K may also be a problem because we have here a retaining ring, and the retaining ring would have a very sharp construction, as you can see here, and this retaining ring, this groove here, can have a very high stress concentration factor on the order of 5. So that stress concentration factor can be a problem even though that the moment is small. So these are points to consider as we move on to complete the design of this shaft. So we're going to go through the same procedure, assuming that a standard radius of the fillet at the root of the keyway is 2%, and that gives us a small value for D. And then we go back to find again the static and then convert it to the fatigue, corresponding fatigue stress concentration factors, both in tension and in shear. And once we do that, then we find the corresponding von Mises values for the alternating stress and the mean stress at that point, and check for the safety factor. Now, when we look at the safety factor here, you find that the safety factor at point K is kind of low, like 1.17, and the required value is not less than 1.5. So we actually, although this point doesn't have the highest moment, but because of the stress concentration factors and the need to transmit torque, showed that it is more critical, so it can actually fail than the shoulder point that we analyzed before. So we have a dilemma. Okay, so how to do it? We can do it two ways: either to increase the size of the shaft, the one that we started with, and then redo the problem, or go back and select a material that is has higher ultimate strength and therefore will have a larger endurance limit and guarantee that the value of the safety factor at the keyway for that particular gear satisfies design requirement. So we're going to do the second option, and when we do this second option, we will have to choose a more expensive steel, and that more expensive steel is 1050 cold drawn. Ultimate strength is 100, and then you go through the procedure to find the endurance limit. You find it 33.3, which is compared to 27. The earlier one, or 25, as we did before, is higher. And then you go through the same design process for the things that need to be changed, which is the alternating stress only. Then you find that the fatigue design factor of safety is improved and it's 1.54. Therefore, we don't need to do any more. Finally, we check at point K, because point K, as I mentioned, it has a flat bottom groove that can have very high stress concentration factor. So when you start with the Kf equals Kt equals 5 for the retaining ring, that's pretty large amplification factor for the alternating stress at this point. So it changes to 28.4, and then when you look at the fatigue safety factor, you find that is really low, 1.17, even though it doesn't have any torque on it, so just from the bending. Thus, we have a problem here we have to solve. And the solution that we have is to be a little bit more realistic. Instead of redesigning finding another steel, then we actually look carefully at the retaining ring and the way that is machined. So the way that it worked here is that we go to globalspec.com and look for groove specifications for the retaining ring, and we know that the shaft diameter is 1.625. Once we go there, maybe some of you will go, you find that it gives you a width of 68 mils and a depth of 48 mils, and the corner radius is 10 mils. And with that, you find that the static stress concentration factors KT is not exactly 5, it's 4.3, and when you use the fact that you get some stress relief from plasticity, which is embodied in the factor Q, the notch sensitivity factor, that reduces the effective stress concentration factor to 3.15. And you redo the calculations for alternating stress, and you find that the factor of safety is reduced, is now, we have a factor of safety of 1.86, which is well above the design requirements. So we have learned now how to to satisfy the design requirements at all critical points along the shaft, and therefore we can list now the diameters, since we don't have any reason to kind of save material on the left side of the shaft. Even though the moments are small, we're going to assume that the left side of the shaft is the same as the right side. It's easier for machining, and that you can finally find that D1 is equal to D7 equals to 1 inch. That's where we have the roller bearings. D2 equals to D4 equals 1.4, and that is by kind of a judicious reduction of the 1.62 as the critical value, and this is upped by a ratio of 1.2 to the largest diameter or the largest size that is available. And therefore we have now complete specifications of the dimensions of the shaft, and we're ready to move on to the next stage of the design, which is obviously going to be calculations of deflections and calculations of critical speeds and so forth, as we move on to the next ideas for completing the design of this